Chayanwal. And this is Professor Arnab Bhattacharya. He doesn't need introduction, but I will introduce him formally. He's a Center Director of Homi Bhabha's Center for Science Education, and he's also a professor in Department of Condensed Matter Physics. And he's also a chair, Science Popularization and Outreach Committee of the AFR. And today he's going to talk about some silly question. So Arnab, all yours.
Thank you so much, Rahman. Thank you. So it's always a pleasure to be at Chayanwal. And today we are going to be looking at just all kinds of stupid questions and to try and find easy ways to get approximate answers, if not exact answers. So what are we doing? Why are we doing? Now, let me just share the screen so I can get started. Oops, sorry. Wait. Okay, so let's see. I hope online audience, you can hear me. And the only way we can get your questions and comments is on the chat. So please put your questions, comments, feedback, etc. on the YouTube chat. And we have somebody looking at the YouTube channel who will, tell me about them. Now, while we get started, you may have seen the poster, which may have encouraged you to come for this. So listen to this. It's basically looking at all kinds of questions which we try to answer with some numbers, and how do we try and estimate those numbers. So that's what it is. And let's go ahead. Now, the room doesn't have a blackboard, and I will have to keep switching somehow because I had initially thought I would just do a chalk and talk thing, but let's see how it goes. Okay, so there is a little quiz. Now, the in-person audience has been given little slips of paper which have interesting questions written on them. Can I get one of them so I can read them out for the online audience at least? Rahman, can you give me one of those questions so I can read them out for the online audience? Yeah. So basically, these are questions which just give you a feel for numbers. So the first question is, how far is your home from this venue, Ruparel College? But you can replace it with, how far is your home from your office or school or whatever else? And then a very typical Mumbai question, how long is a local train? And we've taken the example of a 12-coach local train. And then the wavelength of light, which we all see, which is a very useful number to know because it helps you compare with things. The diameter of human hair, the weight of air in a room, surprising. And all of us use mobile phones, but the frequency of operation of these phones, what's the frequency? And then pressures, what's the pressure in a car tire? You fill it when you go fill it, they say 32 or 28 or some number. What is that number? Okay. What is the pressure in an LPG cylinder at home? What is the pressure in an oxygen cylinder that they use in a hospital or someplace? Right? That's pressure. Then there's temperature. How hot is a candle flame? How hot is the cooking gas flame that we use? Then we can go on to make estimates of large numbers where we really don't know how to get they're not intuitive. So for example, how much power does the entire city consume? Or how many ATM machines are there in India? Or how many messages are there on WhatsApp every day? Okay, things like this, which are what I call the silly questions or stupid question, where there is no correct answer, we don't know the exact number, but maybe we can think of how to find these numbers. Okay, so on that note, we'll get started. And by the time we end, hopefully you'll have enough inputs to solve the problem at the back of the page. The problem at the back of the page is very simple. You are a robber, okay? And you have managed to break into the bank where all the money of the world is stored. Well, in India, let's say it's a reserve bank. And there is lots of gold stored there. And there's lots of bundles of 500 rupee notes stored there. Okay. You are a person of average physical fitness. That means you're not an Olympic weightlifter. You have an average backpack with you. You don't have one of these huge Flipkart delivery agents backpacks. Now you want to maximize the amount of money. And you know that you need to be able to run with that backpack. Right? Otherwise, if you're going to not be able to drag it, then somebody will catch you very soon. So to maximize your loot, what would you do? Would you take some gold, some notes, all gold, all notes? So you have a constraint on your bag and yourself. You want to make as much money as you can. You want to get away from there quickly. What would you do? Okay, think about it. Don't write too many equations and solve them. Based on what we covered today, I think you'll be able to figure out how to tackle such problems when you get them. Okay, so let's move on. First thing I should tell you that these are just some randomly chosen examples that we are doing today. I am absolutely terrible in mathematics. I am not going to be able to write any equations for what we are doing. There are lots of fantastic resources online that we can use. And I would recommend a few things. So there is a very, very nice MIT open courseware, which is available online for free. It's called The Art of Approximation in Science and Engineering. And that was developed for a book by Sanjay Mahajan called The Art of Insight in Science and Engineering. And there is a very nice, beautiful old gem from Vigyan Prasar. I must thank Rachna at NCRT for pointing this out to me. Vigyan Prasar is sadly dead, but it's a very nice book called Fermi Problems or The Art of Estimation. And if you're on Google or ChatGPT or something, you can just Google Fermi problems and you'll get lots of very interesting sites that talk about these Fermi problems. Okay, so now let's move on. Now, of course, you're saying, okay, TFR is full of scientists. What are these scientists? Scientists always talk about accuracy and precision and getting exact numbers and doing the calculations and all. But unfortunately, the real world is very messy. It's very complex. There are too many things that things depend on. There are too many parameters. And this makes exact calculations very hard to do. So most often, if you want to get insight, it's often more useful not to do the problem exactly, but to do it approximately. To do it approximately, and this is very useful for these real world, what I call stupid questions. But it's useful for all kinds of problems. And in fact, in physics, physicists are sort of known to make these approximations where they discard complexity and they think of everything. The famous example of consider a spherical cow in a vacuum, right? So they make examples where they eliminate everything else in order to get to the basics of what is happening. And we will try to do some things like this. Okay, so if you don't believe me, you can listen to the gurus. Feynman said that everything we know is only some kind of approximation to the truth, because we know that we do not know all the laws that exist. So because of this, whatever you do is an approximation. And another quote is from Bertrand Russell, who said that although this may seem like a paradox, all exact science is dominated by the idea of approximation. When a man tells you that he knows the exact truth about anything, you are safe in inferring that he is an inexact man. Okay, so that's Russell. You've heard Feynman. So let's go ahead. So these things, many of these things are called Fermi problems. They are called Fermi problems because they were made famous by Enrico Fermi. And Enrico Fermi, the first Fermi problem that he actually solved was, he was there as part of the team. Of course, he is the guy who started this nuclear age and the first fission pile and all this. He was also part of the Manhattan Project where they built the first nuclear bomb. And while people had lots of sensors and everything near the test site to calculate what would be the yield of this explosive, this first device, Fermi did a very simple experiment. He was about, quite far away, and he dropped some pieces of paper. And by seeing how far the paper flew, he estimated it. He got 10 kilotons of TNT, and the final value was somewhere between 18 and 21. So this is a classic Fermi problem that he set up. Then he made many other problems, and one of the famous problems he had was how many piano, which he asked in exams in Chicago, how many piano tuners are there in the city of Chicago? Now, obviously, we are not in Chicago, and we are not familiar with piano tuners, perhaps. So we will take more examples which are local to us in Mumbai over here. Okay, so I'm going to skip this. I have the how he estimated the bomb thing. If you want to know how he estimated the yield of the bomb, ask me later. I can get to it. Okay. So what we're going to do right now is look at some simple observations which combined with some physical reasoning will give you very powerful ways of estimating things. Okay, and we will need some things. First thing, we are doing only order of magnitude calculations. Okay, we are not going to try and get any more precise, right? And we will use only 3 numbers. there is only 3 numbers you need to know. The numbers are 1, few, and 10. What is few? Well, anything between 3 and 7 is few. Few is defined as few multiplied by few gives you a 10. So if I have 2 fews, I will cancel them and write 10. If I have a few on top and a few on at the bottom of some division, I will cancel them out. Okay. And the idea is you divide and conquer. Divide and conquer means you break up the problem into as many smaller subparts as possible. Yes, we will make mistakes in them, but hopefully if there are enough small subparts, all the mistakes, some of the mistakes will cancel out. So we will get a reasonable number at the end. That's the philosophy. And if we can't do this, there's another thing which can say, okay, I don't know how to calculate this, but I know it must be less than this, right? If I need to know how many people in Mumbai are doing something, it must be less than the population of Mumbai. If how many people in Mumbai are doing something, it must be more than the number of people in this room, right? So we can always find something which is a lower bound, something which is an upper bound, and then take the mean. Now you don't add them and divide by 2. You usually take what is called the geometric mean. You multiply them and take the square root. That's the trick here. And then you can use physical intuition. I'll give you an idea of this. You can use a dimension and analysis, give you an idea of this later. And finally, you should always ask yourself, is the answer I'm getting reasonable? If you did some answer which you were asking how many people in Mumbai do something and you get an answer of 100 million, well, there are not 100 million people in Mumbai. So you know that I've made a mistake somewhere, right? So just common sense check your answer. And it is good, maybe not for today, but in general, it is good to know some numbers and some measurements, some rulers that you need. Okay. So some of these are your hand, a perfectly good ruler. Okay. Now I hope you've seen a ruler in a geometry box, 15 centimeter, 6-inch ruler. But even without that, your little finger, slightly bigger, but almost it's a good approximation of 1 centimeter. Your thumb, slightly thicker, 2 centimeters. If you take 3 fingers, 5 centimeters. Your fist, approximately 10 centimeters. Now the thing is, most human beings tend to be similar sized. And hence it works. It doesn't matter. You might be off by a little bit. There might be a 10% variation, but it's not bad. And by the way, your hand is not only a good ruler, it's a good protractor as well. If I hold my hand up like this, that angle that a finger would subtend is 1 degree. If I hold up my thumb, it's around a little more than 1 degree. It's about 2 degrees. If I do this, it's about 5 degrees. If I do that, that's about going to be, my fist extended is going to be 10 degrees. So you can even estimate angles between objects by your thumb, by your hand. Okay. Crude, very crude. Let me tell you, this is very crude. It's not accurate. But often to make measurements, if you extend that's about 20. It's about 20 and that will be about 20 degrees as well. Okay. You can check 20, 40, 60. You can see whether you can, how many degrees it takes. Okay. So your hand and fingers are very, very useful. Then as well, I come from the physics background. So as physicists, and these numbers are useful for many things, it's also good to know, some other numbers, right? Now a day, how many seconds does a day have? When a minute has 60 seconds multiplied by 60, 3,600 in an hour multiplied by 24, it's around 10 to the 5. A year is around 10 to the 7. If you want to be more accurate, it happens to be very close to pi into 10 to the 7. Pi into 10 to the 7 seconds is a year. Okay. Age of the universe, good to know, 14 billion years. So if you get some answer which is more than that, be careful because you can't have things which are older than the age of the universe, right? It's a good number to check. Then it's good to know that the radius of the earth is around 6,000 kilometers. If you don't know this, we can figure it out, but good to know this. Also, the Earth-Sun distance is about 1.5 million kilometers, at least 1 million kilometers. That's the order of magnitude. Similarly, when you're dealing with solids and objects, the distance between atoms is a few angstroms. Angstrom is 1/10 of a nanometer, right? Similarly, human hair, every time people compare it, is it thicker than your hair, thinner than your hair? Hair is between 50 to 100 microns, 0.01 centimeters, right? That's how it is. One speed you should know, and here there is an equal to sign because this is close to being exact. Speed of light, 3 into 10 to the 8 meters per second. Okay. Now, energy units, often you get units in joules and kilograms and all that, but those are not very useful numbers. So here expressed, if you multiply it by c squared, because mc squared is an energy, you will get half an MeV. Okay, half MeV is thing, and then you know that the proton is like 2000 times more something, so you'll get a number like 1000. Then Planck's constant, again Planck's constant by itself, Planck's constant, Avogadro's number, K, these never come by themselves. K always comes as KT. Okay, I forgot to add KT in this. So for Planck's constant, it's better to remember this thing H bar or H cut or whatever you call it. H bar multiplied by C is 200. 200 what units? Electron volt into nanometer, or equivalent, you can call it MeV into Fermi. Fermi is 10 to the minus 15 meters. So depending on if you're in nuclear physics or you're doing atomic physics, nanometers or Fermis, whatever length scale you encounter, 200 MeV Fermi, 200 electron volt nanometer, same thing. Right? Useful, I mean, much more useful when you want to do calculations. Density is very, okay, the other thing in energy is room temperature. Room temperature, the value of KT, K is Boltzmann's constant times temperature. Don't worry, you don't need it. You won't need it till you get to college. Right now, for this lecture, we won't need it. I'm just giving you this in case. It's 25 milli electron volts. Very useful number to know when you compare things. What you might want to know even for today, density of water. Water, 1 gram per milliliter, 1 gram per cubic centimeter, or 1000 kilos per meter cube. 1 meter, 1 meter, 1 meter, meter cube, 1000 kilos water. So a Syntex tank, 1000 liters, weighs 1 ton. Okay. Air, on the other hand, is 1 kilogram per meter cube. Air is 1000 times lighter than water. Air, 1 meter cube is 1 kilo. Now, this immediately tells you the answer to one of the questions over there. What is the weight of air in this room? Right now, if you look at this room, this is at least 10 meters this way, at least 10 meters that way, right? And at least a few meters high. So 10 into 10, 100 into few hundred into 1 is few hundred. The air in this room weighs few hundred kilograms. So the air in the room is much heavier than us. We don't think so, right? But just remember, air weighs 1 kilogram per meter cube. And if you look at the size of typical room, it's a few hundred kilograms. And this is probably more than 10. But anyway, so these numbers are often good to have in your mind. So let's get started. We're going to start with a very simple one. What's the area of Mumbai? Right now, if you really want to do this, you have to take a map and you have to go around the outline of Mumbai and, do it. And well, the coastline is always jagged, and how do you do this? But let's try and see what is the easiest way we can do it. Okay, and now, what's the easiest way to do this now? I switch to this. Okay, menu, Android. You're going to switch the camera. Note. Clean. Okay. So, you know how India looks. India looks something like this, and Mumbai is somewhere here, right? And if you zoom into this place, there is the coastline, and there is Mumbai is a little island. I need to stop screen share. Yeah, just a sec. How do I stop screen share? Okay, I know. Yeah, but I need the escape key for that, which I don't have in the tablet mode. Escape. Stop share. Okay, sorry about that. Okay, online audience, for you again. India looks something like this, and Mumbai is over here. I don't know why I don't have I don't have a black pen. Okay, so if you've seen the map of Mumbai, all I'm going to do is I'm going to assume the map of Mumbai is a triangle like this. Okay, and let's see. On this side, this tip is Kolaba somewhere. Out here, maybe Borivali. Out here is Thane, right? And well, I think Mumbai to Thane is maybe about 30 kilometers. Mumbai to Borivali is how much? 30, 40, right? And this is 20, 25, whatever. I don't care about these numbers. I told you, I know only 3 numbers in life. So what is an area of a triangle? That's all I need to know. Half base into height. Okay. So I have area. Few into 10 is height multiplied by another few into 10 is this. Okay, what happens? Few and few give me a 10, right? 10 into 10 is 100. 100 into 10 is 1000. Divide by 2. (500 kilometer squares is my estimate of the area of Mumbai. Okay, 500 kilometers squared. I can also tell you this will be an underestimate. Why? Because we don't take the exact shape of the thing into account and all that. Okay. Menu. So we were looking at what's the area of Mumbai, and to check it, what I did is I went to Google and what is? Your choice. Sometimes you take it as few, sometimes you take it as, it doesn't matter. For order of magnitude, it won't matter, right? So what I did is I went to Google and asked area of Mumbai. It told me 603 kilometers squared. You got to switch to this camera now if you're doing this. Okay. So area of Mumbai, 603 kilometers squared. Not too bad, 500. We're doing nothing but just doing a simple triangle. Okay. So let's get a little bit more interesting, where you need physical intuition. Okay. I'll not think. So how fast does grass grow? There's grass growing outside, right? And the science question is a grass growth limited by the sunlight or by the water? Now, if you're from Mumbai, you know the answer to this. There's grass everywhere, but it doesn't grow. Monsoons, fatafat, it starts growing. So you know the limitation is water, not sunlight. Okay, that's your physical intuition. So when you calculate this, you know that the answer should come out to be water. And how do I do it if I had to do it? Okay, I know that I get so much sun on the earth, right? And maybe some part of it on the ground. And of course, I need to know the rate at which it's coming. It doesn't shine 24 hours a day. Grass is not growing 24 hours a day. So it grows for so many hours, some fraction of it. Okay. So I know the energy I have from the sunlight. I know photosynthesis is pathetically efficient. So I'll assume like maybe it uses maybe 10% of the energy, 1% of the something, right? Few percent of the energy. So I know how much energy it can get, right? Then I know that, okay, I see if grass grows, it grows like, I mean, I see the TFR lawn. When they don't mow it in monsoon, it grows like this much in a week. So I know it grows by this much. So I know approximately how much it grows every day. I assume grass is carbohydrates. All plant material is carbohydrates, right? So I know to make so much carbohydrate, how much water I need. So I know the water budget for that much of growth. And I know how so you can work these things out. It's possible to work out things like this. But at the end of the day, if all you want to know is this, you know by your experience that it's water. So physical intuition, don't forget physical intuition. Don't just do an equation or do some calculation on and then the calculation gave you this, it must be right. Think about it and see, is it correct or not? Okay, that's the only reason to show you this. Now we multiplied length and breadth for area. Let's do volume. What is a volume of a 100-rupee note? And this will be very useful to you when you want to rob a bank. Okay. So what is a volume of a 100-rupee note? 500 is 100 rupee note. Okay. 100 rupee note. What's the volume? What do we need to know? Is it one, how much is 1 centimeter? Is it 1 centimeter? Is it 1 meter? 10 centimeter. So this is approximately 10. This is few, right? This part is easy, few and 10. The difficult part is the thickness. Right? I'm trying to do this in the head so that we don't have to do this screen switching and all this stuff. Okay. Now, what is the thickness? Let's assume this is normal paper. It's probably slightly thicker than normal paper. Now, I need to know what is the thickness of a sheet of paper. I don't know. But what do I know? Well, some of you may know that if you're rich, earlier you used to go to bank and get bundles of notes. The bundle was approximately how thick? From that, you can figure out that 100 notes occupied this much space. But more than that, these days, probably you see paper for printers and paper, they come in reams. I don't know what a ream is. That's 5, right? But I know that a ream of paper is about this thick. So few hundred papers, a ream contains few hundred papers. Few hundred papers are a few centimeters thick. So paper is 1 upon 100 centimeter thick. Right? This you can figure out not doing anything. Paper, or you can also fold the paper and see what you get. Paper is 1 upon 100 centimeter thick. So I have 10 multiplied by few 10 divided by 100. So it's few divided by 10. So that will be like half, right? Half a cubic centimeter. Now remember, what is 1 milliliter, 1 centimeter, 1 cent. You can imagine, like 1 milliliter is like maybe the volume of 1 digit over here. So we are saying a note is half of that. Okay, now I hope central bank will give me my money back. You can also try and keep folding a paper till you can't fold it anymore. So I thought, can I make a cube out of my note? And I did. That's 100 rupees in a little tiny thing. And it's about half a, it's not too bad. So our estimate was not too bad that this thing, I mean, you can probably fold it one more time to make it slightly bigger than, this is less than 1, but these are bigger than 1. It's certainly bigger than my finger, right? Wider than my finger. So I couldn't fold it that small, but I also wanted to do it in a way that the bank would believe me if I opened it up and gave it to them and exchange the note. Anyway, so you can figure out the volume of a 100 rupee note. And by the way, the volume of a 500 rupee note will be about the same, right? It's not going to be very different. The 500 and 100 are about the same size. So now you know the volumetric density of how much money do you get per liter. And now you know your backpack is 20 liters, 30 liters, whatever it is. Okay. Now you also got to figure out the weight. How much does paper weigh? Can you carry 30 liters of paper on your backpack? Can you carry 30 liters of gold? Right? Anyway, so that's another problem. But this is why I did this one. So we've now added one more thing. Now, so here again, we could have gone wrong in the length, breadth, width. But finally, hopefully, if we have made some errors, they have compensated it out. And we got an answer which is not too far from the okay, I don't know who is GS 3.14, if you're watching us or not, or if you're here. This came on Instagram. I had said people can ask questions. The question was, if we take all school uniforms in Mumbai and lay them flat, how much area would it cover? Okay. So now we have to work this out. I have tried to work some of these things out. Okay, so maybe for this, I will switch so we can write some numbers down. Okay, so I have to stop share, menu, Android, note, clean. Okay, so we're going to try and find out. We are interested in the area. So first I need to know how many kids are there in school and how many school uniforms there are. What is the area of a school uniform? Then we can figure out the total number of them. So now let's look at Mumbai. What's the population of Mumbai? 2 CR. 2 CR is, so population 20 million. Okay. That's probably Mumbai plus metropolitan region and everything else. Fine, we'll do it with this. We'll take 20 million. Now, obviously, all the 20 million are not going to school. Right? There's some distribution of age. There is some fraction of people that go to school. Okay. 20% go to school. Now, 20 is not a number in my thing. It's either 110. So I'm going to assume that of this 10% or 2 million go to school. You can make it 3 million, 4 million. It's not going to make a difference. 2 million, 10% go to school. Okay. And let's assume that all of them wear uniforms. There might be some fancy schools where they don't wear uniforms, but let's assume everybody wears a uniform. Okay. And uniforms, whether it's a shirt, pant, skirt, whatever, they all take the same amount of cloth, approximately the same amount of cloth. Okay. Now, cloth you buy in meters. Now, the width of the roll is also approximately a meter. It's not 10 centimeters. It's not this much. It's close to a meter. So, I don't know how much you need to make a school uniform. Maybe you need slightly more than a meter, but you don't need 3-4 meters, and you certainly don't need 10 meters, right? You don't need this whole length of stage to make a uniform. You don't need half the stage either. So I am going to assume that uniform is 1 meter squared. 1 meter squared cloth I need to make the uniform. Okay. So if I need 1 meter square of cloth to make a uniform and I have 2 million kids, the total area of uniform is 2 million meter squared. Okay. How much is this? Not a number in our head, no? So first thing, let's convert to, remember, area of Mumbai is 500 kilometers squared. Let's convert this. See, remember million. Thousand into 1,000 is a million, right? And 1,000 meters is a kilometer. So a million meter squared is 2 kilometers squared. Get this? A million meter squared is the same as 2 kilometers squared. So this is basically 2 kilometers squared. Area of Mumbai, 500, 600, whatever. And there are still some people coming in. Okay. So 2 kilometers squared. Now let's look at 2 kilometers squared in terms of, see, generally when people report such things, they'll report in terms of so many times Wankhede Stadium, so many times Oval Maidan, some area that you have in your mind. Okay. So what I will leave you to do is, please come, ma'am, is calculate this in terms of some cricket stadium, Oval Maidan, whatever it is. So let's take, I don't know, what do you want to take? Yes. You had a question. Oh, what is not? Ask. If something is not clear, please ask. Fine. Double it. Okay. These are very approximate things.
Let's say the area of
Ruparel College का क्या वो ground लेंगे नहीं लेंगे? Some people may have come only from here. Oval Maidan is a good thing, no? Everybody knows Oval Maidan. Oval Maidan, Cross Maidan, all these places where they go and protest and have rallies and all these things, right? So if I take a typical place like Oval Maidan, it's probably about, so to get on this side, maybe 500 meters this way, and maybe about 200 meters this way. I'm taking numbers to make my life easy because 5 2s are 10. I love numbers when there are multiples of 10. Cross, same thing, na? Area is going to be about the same. I'm just doing something which is, take Cross Maidan here, it'll be very, Cross Maidan, the shape is a little weird, that's all. But this is going to give me 500 into 200. So 5 2s will give me a 10. So this will be, when I multiply this, this is too fancy for me. I don't know what gives me red and what gives me erase. So 2 5s are 10, 0 0, 0 0 meter squared. And if I do this in, became red. And why is it red? I didn't select the red. I want black, no? I was continuing to write. So this is that many meters squared. We can 0.1 kilometer squared. Somebody said 20 times. So 20 oval maidans worth of, if you're laying out all the uniforms, right? Yes, we've taken, of course, remember when you stitch a uniform, the area is actually double the area. But if you're laying it out, only one surface is visible. That one compensating of the fact that everybody has 2 uniforms. So all these things will cancel. So these are just simple ways of making calculations which you can do. That's why they say back of the envelope calculation. You should not require much space to do it. Whenever possible, see if you can get out factors of 10. Make life easy. Okay, let's go back. So we've looked at uniforms. Okay, there's a more difficult one. This came on WhatsApp. What is the total length of roads in Mumbai? Okay. What is the total length of roads in Mumbai? Now, the problem is there are lots of different kinds of roads. You have expressway, which has so many lanes, freeway, 4 lanes, Western Express Highway, Eastern Express Highway. You have little gullies in the middle of something. Okay, so how do I estimate the total length of roads in Mumbai? So what I'm going to do is, I'm going to do again a very crude estimate. If I look at Mumbai, there are some green regions in Mumbai. There is built up area in Mumbai, houses, whatever, factories, whatever they are. And there are roads in Mumbai. Of course, this is overestimating the roads. If I say the roads are 1/3 of Mumbai, it's overestimating the roads. But let us suppose they are 1/3 of Mumbai. And Mumbai's area was 600. 1/3 will be 200. 200 kilometers squared of area is roads. Now, a road is not 1 meter, right? A road is typically, make it 10 meters. So if 200 kilometers squared Just remember 200 kilometers squared divided by 10 meters will give me the length of the roads. So 200 kilometers squared divided by 0.01 would be 2000, would be 20,000 kilometers of road. That's too much. That's too much. 20,000 kilometers of road is too much. Okay. Can somebody Google what is the length of roads in Mumbai? BMC or someone must have put this information. I have no idea about this. Yeah? 2000 km. When? 2000 seems a bit low to me. 2000 seems a bit low to me because right now, just the expressways themselves, I mean, by the way, they probably consider the expressway as one length of road. In my calculation, given that the expressway is 8 lanes, it would be much more than this. That is one place we may have gone wrong because we are just calculating and they probably calculate only major roads. They don't take into account all the gullies and all the patli gullies are not included in that. So, okay. So we've had BMC's number is 2000. My thing saying that 1/3 of Mumbai's roads is 20,000. So it's somewhere between that. So, 4 squared is 16. Yeah. So if I take these two as my limits, 20,000 too much. Anything is possible. Do it. Let me know what the estimate is. Right. So if I take even 2,000 and 20,000, the mean of that will be around 5,000. Right. So it's okay. I mean, we'll get some number which is not too bad. But anyway, this was a little more difficult because I don't know. Maybe that 1/3 estimate was wrong. We should have taken a lesser estimate. I don't know. Okay. Now let's increase complexity. These are the ones I had on the poster. Question? William, go ahead. Yeah. Sure. So in the moment I got 20,000, I said, no, this is not correct. But I think 2,000 is low though. I don't know how old that number is, but that's one way of doing it. That's the minimum amount of new roads that are, or roads that are repaired in. Correct. Yeah, go ahead. Shout. The fan is on. I can't hear you. Don't try and get into, and that is definitely wrong. Right? Because how did they measure 48.43 and all is like, where did this is like on these railway stations, they say the height of the railway station is 176.53 meters above sea level. Like, that means you're accurate to a centimeter. Is that the height of the writing is more than that? So you can't be, where on that line have you measured it? So, all those, I'm trying to go the other way, make it as inaccurate as possible, not as accurate as possible. Any other questions? Good time to take a break. Yeah. I'm getting a length, na? Area divided by length will give me a length. I'm calculating length of roads. So I was dividing by the breadth of the road. I took 10 meters as the breadth of the road. Well, assuming that the roads have the same density around Oval Maidan as everywhere else, yes, that's another way to do it. So see, there are many ways to do it. And if you do it in multiple ways and you get similar numbers, you're more likely that you have more confidence that you're probably right. Okay, so this is what I had put on the poster. The next few are the ones from the poster itself. How many people are standing in local trains at basically peak hour? 10 a.m. on a weekday, how many people are standing in local trains? Shall we try to work this out? Okay, and this will be followed by how many umbrellas, which is the next thing. How many umbrellas are open in Mumbai at 5 p.m. on a weekday? Okay, ultimately stupid questions. I have no idea what the correct answer is, but let us try. Okay. This is the next question. The third question on the poster was what is coming, but we'll wait for that. The third question on the poster was how many cups of chai are being drunk in Mumbai right now? If you want, we can start with that. I don't mind. Huh? We'll end with that. We'll end with how many cups of chai are being drunk in Mumbai right now. Okay, so first one we are doing is people standing in local trains. So do you want to guess how do we do it? How are we going to try and do this? You want to start with population, okay?
One X is sitting and two X is standing. So you know the number of trains that are moving around at around same rate. So each capacity of the train, so 2X into multiplied with that.
Okay, so you're going to start from down and move up. You're going to start from total population and move down. We can do either. Let me start with that approach. Okay, so Mumbai has 3 railway lines: Western, Central, Harbour. Okay, let's assume all lines are the same length. They are, I mean, maybe about 100 kilometers or so, right? Maybe 40 se zyada hai. So, I mean, even if I take till Kalyan and till, wherever, Virar and something, say 60, 80 kilometers. So let us say that, wait, where are my notes? Better not get this wrong. So, we're going to make some simplifications. All trains are, they're not 12-car trains, they're 10-car trains. Okay. We're going to say that all trains are 10-car trains. You know why I'm doing this? Dividing by 10 is much easier than dividing by 12. Probability of? Yeah, there are 15-car trains, but that would make it even go the other way. Now, it takes about whatever the distance is, say 100 kilometers, right? We'll make it slightly less. It takes about an hour to an hour and a half. Big gang, come, big gangs are also welcome, even if you come late. A lot of space, lots of space. Let people come. We'll start this problem from scratch. No, you're not late for chai. And you're not late for the problem that will calculate how much chai. Wow. Okay, this looks like an invasion, but let's wait for this. Come, please come. So, for those who came in late, what we are trying to do is trying to make some estimates of any kind of question you want to ask. Okay. And we started off with the area of Mumbai. We started off calculating what is the area of Mumbai. And all we did was we took Mumbai as a triangle and said half base into height and we have, oh, by the way, we are going to use only 3 numbers, 1, few and 10. Few squared is 10. So if there is a few and a few, I can cancel it. If there's 2 fews, I multiply and take a power of 10 to get order of magnitude estimates. And currently we are trying to so we calculated the area of Mumbai. We calculated some question which came on Instagram of what is the total area if we take all school uniforms in Mumbai and lay them out. we calculated the length of roads in Mumbai, we calculated some other stuff. Anyway, the volume of $100 note, a 100 rupee note. And now we are trying to figure out at 10 a.m. how many people are standing in local trains in Mumbai. Okay. So, and we've just decided that we are going to take all trains to be 10-car trains and not bara dabba because it's easier to divide by 10. And the train takes about, we said the local, the Central Harbour Western lines are around 100 kilometers. But again, I'm going to make some simplification here that it takes, either I will say it takes 100 kilometers, 100 minutes, but I know it takes about an hour and a half to go to wherever, Virar, Kalyan, something on a fast train. So a little beyond Kalyan. So if you have 90 minutes, right? 90 minutes is what it takes. And the frequency of trains is every 3 minutes that we know, peak hour. So 90 kilometers, 90 minutes, 3-minute frequency. There are 30 trains at any given time on that track. There are 30 trains. Agreed? So now, so there are 30 trains per hour in this thing. Now we need to figure out, obviously the number of people going towards Mumbai in the morning is much more. The trains which are going away from Mumbai, same frequency, but they are kind of empty. Okay. So I have 30 trains multiplied by 10 coaches. And he was saying that double the number of people stand than there are seats. I think there are about 70 seats, 100 and something. Again, round figure, let me say 100 people. 100 people are standing per coach. Okay, this is in the going direction. So this is at any point we have 30,000, 40,000. People who are standing one line going towards Mumbai. The ones who are going away from Mumbai, oh, khali rehta hai. Maybe there are 10 people standing. So we will add another 3,000 here. So we are going to get 33,000. Okay. That's on one line. Multiply by 3 lines. Right. So you have approximately, in my calculation, about 1 lakh people standing at any given time in a train in Mumbai at, I don't know if this is right, wrong, whatever. Yeah. But all those are on the track at that point. Na? At any point, there are 30 trains on the track at this point. And this is probably, I rubbed it off. Okay, sorry. So we had something which showed around 1 lakh, which is probably a lower estimate, but it may be okay because Harbour is not as long a network. But then you have to figure out there is multiple networks. There are things going towards Ambernath, going towards Kasara, etc. It can get more complicated than this, but order of magnitude, it is 10,000 would have been too low. 1 million would have been too high. 1 lakh seems a reasonable number. 100,000. Well, I mean, we've assumed only 10-car trains. We've assumed only 100 people. It's probably more than that at peak hour. Yes. So that's another. Now let's figure it from the other end. 70 lakh travel every day. 7. Okay, what is 70 lakhs? Number of passengers per day? Number of passengers per day. Okay, doesn't matter. Number of passengers per day is 70 lakhs. And this is happening, let us say, in 3.5 hours, right? 1 point something hours in the morning and 1 point something hours in the evening is when all. Okay, then make it 3.5 hours in the morning and 3.5 hours in the evening. So it's 7 hours total, right? 7 hours, 70 lakhs, 10 lakhs per hour is traveling. And I would say most of them are standing. So it will be something less than, something between 1 lakh and 10 lakhs. from that calculation. If we assume that number is, but we don't know whether it's, that's another way of looking at it, but I didn't know the number. So, okay. The second problem we had was, what was the second one? Remember? Umbrellas. Umbrellas is a little bit more open-ended. Okay. So let us say Mumbai metropolitan region. So this is how many this was asked by one of my students. I don't know how many umbrellas are open in Mumbai at 5 p.m. Somebody has asked me the question, I need to give them an answer. Okay. So now, again, I have to divide and get into smaller frame. So clearly, I know an upper bound. Population of MMR region is 20 million. Can't be more than that. Clearly not. All 20 million, let us say, don't come to Mumbai for work. Let's say maybe about, I don't know, 5 million people come to Mumbai for work every day. 5 million people come to Mumbai for work. Few million. I don't know a number called 5. Sorry. Whatever, few million. Add another million to it. It's okay. Still few plus a million is a few. Okay, I don't know why it became red, but whatever. Now, okay. So few million people. Now, not everybody carries umbrellas. Okay. So, some people just don't carry umbrellas. They might use a raincoat or something else. So they might just decide to get wet. Who knows? Or they forgot their umbrella at home. Some people don't carry umbrellas. Some people. So maybe of the few million, I'm going to now reduce this to 1 million people have umbrellas. They have umbrella with them. Right? But not everybody is going to leave office at 5 p.m. They'll have staggered their timings out. Okay. Not everybody is going to leave office at 5 p.m. They will something. But on the other hand, some people may have left earlier and they've reached their station or bus stop and they're walking home from there. That's also there. We need to count them as well. And, if I think 1 million people have umbrellas and some fraction of them is going to be open, my guess will be is then that it is going to be few hundred thousand umbrellas. If it is raining everywhere, if it is raining everywhere in Mumbai at this point in time, at the most you will find few 100,000 umbrellas which are open. That's my upper limit. You can refine the calculation. I'm not claiming that this is anyway, but I think it is definitely more than tens of thousands. That would be too low. And it's certainly not a million umbrellas. I don't think a million umbrellas are open. I don't know if it is possible to ask Google or ChatGPT or something how many umbrellas are sold in Mumbai or something. That's one more way we can figure out that umbrella sales are so much. People probably buy umbrellas once in 2-3 years. So those are the number of umbrellas we have in Mumbai. And then we can figure out what fraction of, that would give you an upper bound. You can't open more umbrellas than that there in Mumbai. So we can work out things in many ways. And finally, I think I can just check it over here. The third problem which was there, which was in the thing which hopefully you're all doing right now is, I hate this. How many cups of chai are people drinking in Mumbai right now? Yeah, I know there are 50 cups being drunk right here, but that's going to be not a good way to start the estimate and scale up. Okay, now let's assume that again, Mumbai metropolitan area, population 20 million. Okay, not everybody drinks chai. Huh? Oh, I need to stop the slide. Sorry. Is that good? Can you see this now? So the question, online audience, is how many cups of chai are being drunk in Mumbai right now? And we have assumed that the population of Mumbai is 20 million. And for convenience, as you can guess, I'm going to make this the population of chai drinkers is 10 million. Oh, half the people are kids and they're not given chai to drink. Another half are, they drink coffee, whatever else. Some drink both, but 10 million people across the region drink chai. Now, how many cups of chai do you drink a day? Some people may drink one, some people are stuck in meetings and they drink chai all day long. Let's assume people drink chai in the morning, in the evening, 2, 3. I know only numbers like few. If it's more than 2, we call it few cups a day. Okay. Now, let us see. All 10 million people, do they drink chai every day? That's okay, a few. That's a big one. So the question is, she's saying she had 5 cups of chai a day in the office, 3 cups at home. If you go to the BRC canteen at any given time, there are 100, 200 people all drinking chai. So I don't know, let us say there are, but I mean, I think few cups is fine. Right now, we are not bothered whether it's 5 or 7 or 3. Few cups a day is fine. Now, when does one drink chai? Let's say, so there are few, right now it is, let us assume everybody is drinking because all the people in office drink chai, all the people at home drink 3 cups of chai. So everybody drinks chai according to her. So we have few into 10 million cups a day. Okay. But let us assume also that people drink chai between 6 a.m. to 9 p.m. Sometime we have to put some time limit. People are not drinking, not these cups. Most chai is not drunk at 2 a.m. in the morning. Some people, yes, I know, but let's say between 6 a.m. to 9. Let's put some reasonable times. लोग सुबह उठ के चाय पीते हैं 6 a.m. Suppose we put some time limit like this. So we have a 15-hour window. There's a 15-hour window in which this chai is being consumed. Right? So then if it is a few million cups in this time, we can figure out how many cups per hour are being consumed. Right? And hence, we can then figure out it takes at least a minute to drink chai. So we can then... the distribution is not uniform. If I had a uniform distribution, I would say that there would be sorry, if you distributed it uniformly, then there are so many thousand cups being drunk per minute, and then there are so many 100 cups being drunk per second. But that is usually going to be peaked in the morning, peaked in the afternoon at tea time, peaked in, there'll be some peaks in it. It's not uniformly distributed. I mean, yes, there are some places where people are drinking chai ki tapri, where people are drinking chai all the day, but certainly it is not uniformly distributed. But you can do such a calculation, and I get a few thousand cups per second are being drunk in Mumbai. Every second, few thousand people are drinking chai at any given point. At? Yeah. Yeah, I mean, if you divide it through the day, it's few thousand, so it's probably much more at peak periods. Anyway, that was a stupid example. Now, finally, oh wow, we've exceeded the. Can I take 10 more minutes? You can ask questions also, so I want to leave time for that. But I want to, I told you in the beginning that there are some things that often help us with these calculations, and sometimes we can use dimensional arguments, and sometimes we can use some kind of physical assumptions and things. So now I want to ask you, how high do animals jump? Small animals, insects, humans, dogs, cats, whatever. How high do animals jump? Does it depend on their mass? Does it depend on their size? Does it depend on what? Muscle power, whatever. Okay. So we want to figure out how high do animals jump, and we will start with the spherical cow model. We will start with a very simple model which is limited by energy. Okay, if I jump to a height h, I need to have the energy to jump to a height h. Okay, so the simplest model is I'm going to jump to a height h, and I will need some energy to do that. We'll see how that scales. Now, I may have enough energy, but to jump, I need to be able to suddenly lift off the ground. I need power. I need to deliver that energy in the time that I take to jump. So I may have energy, but I may never get to my energy limited height because I'm limited by the power. And we can add, right now we are jumping in vacuum, but we can then add air resistance and other things and slowly complicate the problem. Okay, so I'm going to see how animals jump. And let me ask you first, before doing this, do you think that lighter animals, smaller animals jump to a higher height than heavier animals, or do heavier animals jump higher? Lighter ones, intuitive, right? Let's do some calculations. Okay? All right? That'll be the last example. So I will stop this. And I will have to go back to the board. So, animals jump. Animals can be humans, kangaroos, insects, whatever, right? We are going to make some assumptions. Assumption is we are jumping from a standing position. For animals that don't stand, we are jumping from rest. We are not running and jumping. Running and jumping changes the physics completely, because then I can store energy while I'm running, kinetic energy, and then use it to somehow jump higher. Or if I'm jumping with a stick, I can pole vault, right? so in high jump, I use my energy of running to actually give me energy to go over the bar. You can't jump that high if you're just jumping from rest. If I have a stick, I'm running with the stick, I bend the stick, put energy in the stick, that stick straightens up, it releases the energy when it's straightening up and throws me over a bar for pole. Those are all different things. Right now, very simple model of jumping from rest, and it's going to be a very, very, very hand waving. So, okay. So I want to find how does power scale, or how does the energy scale as a function. We'll first start with energy of a thing, and I'm neglecting the shape of the animal, 2 legs, 4 legs. All that is Now we all know that all of life depends on DNA cells. We are going to assume that all life has the same kind of muscles. The muscles that we have are the same as the muscles, the material that makes the muscles the same as the muscles in a horse or a kangaroo or an insect or whatever. So the energy that per muscle weight is going to be the same. Assumption. And nobody's going to the gym and training and all that stuff. So all muscles are, equally bad or equally good. Okay. So now I have some animal, it has a mass M. And a size L. Okay. And I want to find that this guy is going to jump to a height H. Some height H, it will jump. Okay. H equal to jump height. I don't know why this does it. Okay. So question is, jump depends on, how does jump depend on mass? Does it depend on mass squared, square root of mass cube? How does it depend on mass? Okay, simplest thing. And we are just going to take into account the energy. So if I have to jump to a height H, the energy required there must be something that you touch it and it converts it to a marker. And I don't know what it is. The energy I need to jump to a height is mgh, mass into g into the h, potential energy at a height h. So far, so good. Now, I don't care about equality and all. I'm just trying to find out what does it depend on. Okay. I can either carry this g with me, like extra clothes you take on a trip and you bring back without using it, because eventually it'll all cancel. The g won't depend on it. All I need to know is from this that E required depends on M H. It depends on M and H. So the more the M, I'll require more energy. The more the height, I'll require more energy. Okay, that's the E that I require. Now, what is the E available? What is the energy that's available? The energy that is available is going to depend on the amount of muscle I have. Correct? Right now, all animals are spheres. We don't know whether the animal does not have hands, legs, back, front, nothing. It's a sphere. Simple approximation, animal has a size L and a mass M. And right now my animal is 100% muscle, right? It is going to depend on basically the amount of muscle, right? Some amount of muscle. The muscle is what given here. The amount of muscle is going to be some factor, I don't know, some whatever, it's some fraction of the total mass. I am assuming that this fraction is the same for all animals. If this fraction is the same for all animals, then E available is proportional to M. Correct? If E available is proportional to M and E required is proportional to H, I can equate them. This has to be equal to this. Okay? Which means that MH has to be proportional to M, which tells you that H has to be proportional to M to the 0. H cannot be dependent on M. And this tells you that all animals jump to the same height. Doesn't seem right. If this is true, this will be H to the 0, M to the 0. It can't have an M dependence basically. If M has to be proportional to M multiplied by something proportional to M, this guy cannot be dependent on M. This has to be independent of M to the power 0. So height does not depend on M. All animals jump to the same height. You don't believe me? So I need to go back. Okay. So here is data. This is the mass of an animal. You have a human, you have a locust, a beetle, a flea. At this range, these are the typical heights that they jump in centimeters. This is 10 power minus 3 a milligram for a flea versus 10 power 5, 100 kilograms max humans. Okay. There is an 8 order of magnitude difference on the x-axis. The x-axis has an 8 order of magnitude difference. But here, it's within an order of magnitude. So as you see, to 0th order, all animals, regardless of their mass, jump to the same height. Okay. However, you notice that these guys seem to be lesser than here. There seems to be some trend. And we will look at this because so far we have done the simplest approximation. We have just looked at, do I have the energy to jump to a right H? Shall we slowly add some complexity to this? Okay. We will try and understand why the smaller guys are disadvantaged in jumping. So our simplest thing was energy. That was the thing we got from energy. Now the second thing I can add to this is, are you switching to this camera? Now, my muscles may give me enough energy to jump to that height, but the question is, can they deliver the energy fast enough? So the next thing I'm going to look at is power. Okay. So how does power scale with the size of the animal? So the power is going to be the energy that I need to jump to h, depending over or divided by the so the energy I need to jump to an height divided the time in which I can deliver this energy. Okay. So this I know E is, we've said this is E is proportional to mgh. Okay. And M depends on the animal. M is proportional to the volume of the animal. All animals are made of water. Density of all animals is 1. They're all made of 90% of is water, right? So if you in doubt anything with animals, density 1. So we are essentially mass is proportional to volume, some density. Okay. So the energy I need to jump depends on L cubed volume. Now, what about the delivery time? The only time I can deliver energy is when I'm in contact with the ground. Once I've gone off the ground, I can't. I have to push back to the ground to get that reaction. So only when I'm in contact with the ground do I get the energy. Now, what do? How do I jump? I crouch and I lift off. Agreed? Once I lift off, I can't get any more. I'm off. Okay, so now what I need to figure out is this time of delivery. This I have done. Time. So I will crouch and jump off, and time will be essentially distance by speed. So the extension distance divided by the extent by the speed. I can do it in the faster I can do it in, I'll get more. So what is the maximum extension distance I can have? The length of the animal. Right? So this, the numerator out there, by the way, these are very, very crude approximations. Please, don't get me that this is not exact. Extension distance is going to be proportional to L. Typically, that's the maximum extension I can do is my own length. Yeah. Now, what about the speed? The maximum speed I have is the speed when I take off. Okay. So, what is this? Okay. So, I'm going to now have to erase some more space here. Now, if I take off this mgh energy, eventually I need that much energy. This energy is going to be my kinetic energy, which is half mv squared, right? So I'm going to remove the equality and just make it proportional to mv squared. Energy takeoff. This is takeoff energy. Is proportional to some mv squared. Just because initial kinetic has to be a final potential. Okay. And if I equate the two, so these have to be the same. So if I equate the two, V is going to be proportional to square root of h from these two. Right? So this velocity is independent of the size of the animal. There's no L dependence in this. If I equate this and get the velocity for the speed is independent of L. right? So the speed is independent of L. It depends only on time. Extension distance is L. So your this power term, the dependence of power on top, you will get an L cubed. The time has a factor of just an L. And this is going to be giving me an L squared. What is more interesting is power per unit. What? If I erase, it becomes red. Yeah, but I don't know why the thickness keeps changing and various things keep changing. I don't like it to be. It's this. Okay. All right. So power to mass, which is what is important, right? This is going as 1 by L, which means small animals find it difficult to jump to their energy limited height. Okay. Now, what do? You see insects jump. Insects have developed a brilliant way to do it. They have shells. Insects slowly bend their body and then suddenly release that energy. So you release it, you gather the energy slowly, and then you like click beetles and all, they'll suddenly jump off. So they are storing the energy and suddenly releasing it. So they have much more time in which they store, but they release it much quicker. That's how they beat it. But they are in trouble for something much more difficult, which we have not looked at so far, which is air resistance. Okay. Now, smaller animals are going to be far more susceptible to air resistance than humans. When I jump, air resistance is not important. When a flea jumps, air resistance kills it. That's why you see those data points are down. Now, the problem is, if you have to do drag and calculate air resistance, technically you'd have to solve the Navier-Stokes equation, you'll have to solve the continuity equation, it'll be a mess. We will need 100 sessions to cover it. And that too, we may not be able to do it. It's one of the more difficult things in physics. But we could again adopt our attitude of trying something super simple, hand waving, to see why do smaller animals have great difficulty in. Now, suppose I am an animal with an area A. I'm a circular disc. I'm an animal with an area A. I'm moving with some velocity V. Okay. So I'm moving through the air. I moved a distance D, right? At a velocity, correct? A velocity V, I have a cross-sectional area A, I'm moving through the air. Okay. What have I done? I have to sweep out a volume of air. The volume of air I displace. I don't know what to do with this here. If you press it, it becomes red. Okay, don't press it. Yeah, you're right. No. Now the erase also doesn't work. Okay, whatever. A times D is the volume, area and the distance. That's the volume. And the mass is the density of air into A into D. So far, so good. That's the amount of mass of air I have to push out of the way if I have to move a distance D. Correct? Now, if I have to push this mass of air away, I'm going to give this mass of air also some energy, which is coming from my energy. So the kinetic energy is going to be proportional to rho A it's going to be proportional to V squared, mv squared, half, forget those terms of half and all. It's basically proportional to V squared. Okay. So that's energy. Energy I can think of, please, I'm just doing dimensional analysis here. If you're doing Navier-Stokes and all, you have to do a very complex way before you come to this point. I can think of energy as force into distance, right? Which means I can, now is a good time to change. I can think of this energy I need to move that air as some kind of a drag force into a distance. Dimensionally, this has a force. Energy is force into distance. So the drag force is going as square of the velocity. Okay. And now the energy and the drag wait, I'm missing a term. I have missed a term somewhere. Just hang on. No, maybe I'm okay. I don't know. Yes. V squared is there, no? Correct. So energy in the drag is this. So if I do this thing, which is the energy required for the jump and the energy that I have to spend in drag. So this is rho A V square D divided by the energy required is mgh, which is the same as, these are proportionalities, mv squared. So this v square and v square will go. So this is, and the d when I jump, this d is h. So to jump to a height h, to jump to a height h, this is going to be a h by m. Okay. Now, h we've seen does not, that's the height I'm jumping to. It's got nothing to do with my size. Okay. A is, this is proportional, A is proportional to L squared, M is proportional to L cubed, right? So again, the energy drag dependent and the energy required has a 1 by L in this. So smaller animals face much more drag. And if I, of course, all I'm telling you is smaller animals have much more drag. I haven't told you what is small. Smaller. We haven't said what is small. To see what is small, I can now compare the masses. Right? I'm just going to clean this. Just remember this 1 by L is what we got, that smaller animals have more drag. But what is small? If I compare rho air into the L squared into H, which was a numerator there, and the denominator is which is basically rho animal. Correct? This was that ratio. This is E, this is the same E drag. Let's check. Is this okay? Yes. See, this is E drag by E. E by E is a dimensionless thing. So that's it. Better be dimensionless. So we have basically rho air by rho animal into H upon L. All right. Now rho air we know is 1. rho animal is 1000. Rho animal is water, it's 1000 into H by L. Now, H is the same for all animals. We're all animals jumped to the same height, right? But for a human being, L is 1 meter. For a small insect, L is 1 millimeter. Right? So for a human being, L is 1 meter. For a small insect, L is 1 millimeter, 1000 times difference. Which means a small animal, the insect, faces 1000 times more drag than a human does. So for a human, this is 1 by 1000. The amount of energy expended in drag is 1 by 1000. But if this becomes very small, you expend almost the same amount of energy in the drag compared to the energy you're spending in your jump. And this is why small animals can't jump very high, because they lose things to drag. This is only a very hand-waving, dimensional way of arguing it out. We've not solved the real equations that you need to do this, but this is just to give you a flavor and idea that you can actually start off with relatively simple ideas, spherical cow, start adding refinements to it, and get to some interesting observations, which explain what happens in the world around you without getting into exact numbers or any. We've not gone into differential equations, we've not integrated anything, we've not done anything of that sort here. Okay. So this is basically what I want to leave you with, is that sometimes asking stupid questions and trying to just argue your way out of it is a fun way to get insights into the world around us, which may give us right answers, may not give us right answers, but often will lead you to the right, or at least an order of magnitude to the right answer, or to allowing you to argue in terms of things about why certain things behave in a certain way. Okay, I have taken way more time than I thought. I should give you time for questions. So I'm going to stop here, and yeah, we can take whatever questions you can take questions from online. Yeah.
Any real life example
Of
approximation currently in scientific?
I think in all scientific research, we generally always start off by finding an approximate thing to tell us where we are before we refine it. So I think it's used pretty much everywhere. I mean, see, for example, I know I am a semiconductor physicist, right? I have to figure out what are the thicknesses of layers that I will need to grow to make a certain structure. I can, of course, solve. You want me to switch this off? This is too bright. You want me to switch it off? We can do that. I can always solve equations. I have to solve the Poisson-Schrodinger equation and all to figure out what's the thicknesses of layers I want. But for simplicity, I can treat it as electrons in this thing as particle in a box and find some approximate answer and use that as a starting point and then refine it. And that is what most people do in all cases. Nobody ever starts off by solving the most complex situation first. Okay, any other questions?
From online.
Okay, then we can stop online and we can just have a more informal gathering here, and then we don't need all this. All right, online audience, thank you very much. Just to tell you that our next session, the first Sunday of August at Prithvi, is going to be on music and mathematics in a way, connecting why do we find certain combination of notes more pleasing to the ear and all. It's looking at patterns in music connecting to mathematics. That's what is happening 2 weeks from now, first Sunday of August at Prithvi Theatre in Juhu. And on that note, we'll stop the live stream.